Hello, this is Professor Kernler again. This video we're looking at section 16.3. We're doing double integrals, but now in polar coordinates. I think we're going to do two videos for this section, refreshing your memory about polar coordinates, and then introducing and developing the technique for how to do double integrals in polar coordinates. And then in the second video, we'll do, I think, 3 examples. So apologize for losing all pretense for dressing up here. I'm wearing my coronavirus pandemic inspired shirt here for today. So we're going to knock out these 2 videos. First one here, let's take a look. We need to first, refresh our memory about polar coordinates. So if we think about rectangular coordinates, we have a point here, x, y. It's some horizontal position x and some vertical position y. In polar coordinates, what we do is we have a radius, that is not a straight line, a radius, not much better, from the origin, and then an angle theta from the positive x-axis. So, for example here, if we have the point 5, negative 5, let's see here, where would that be? That would be 5, negative 5 would be down here. That point in polar coordinates would be 5 square root of 2, that's how far it is from the origin. And then an angle, there's a variety of responses there, but we could put negative pi over 4. And then, like the equation of a circle, x squared plus y squared equals 9, that's a circle radius 3. Well, what that means is that the r is a constant 3 and the angle can go throughout all of the angles, and so that's a simple equation of polar coordinates, r equals 3. The conversion between the two systems, if you have r and theta, you can figure out x and y. And then if you have y and x, you can use the fact that tangent theta is y over x. You have to be careful just doing the arctangent because it depends on which quadrant you are in for your y and x, so you might have to add pi to that depending on where you are. And then of course you can figure out the r because of the Pythagorean theorem. So we are interested in looking at double integrals. So let's take a second and look at some regions that are in the xy plane or in the r theta plane and kind of compare what those would be in rectangular coordinates and then look at some other examples in polar coordinates. The first 2 on the left are going to be rectangular. So here, describing this first one on the top left, that would be saying that x is between 2 and 5, and that y is between 2 and 6. On the bottom one, we could say, let's see, we could do it this way. If we look at this here, y is equal to negative 6/5 x plus 6. That would be that equation for that line. And so we can say y is between 0 and negative 6/5 x plus 6, and x is between 0 and 5. So relatively simple regions in the rectangular coordinate system. Up here for the top right in polar coordinates, we have r is between 0 and 2. And then theta sweeps out all the angles between 0 and pi. And then think of that next one, that seems pretty complex. In a rectangular coordinate system, you have to go like between 2 circles, and you have to do top half and bottom half. But here, all you're saying is that r is between 3 and 5, and theta goes all the way around, and so theta is between 0 and 2 pi. So sometimes if we're integrating over a region, if it's circular, it might be easier to use polar coordinates rather than rectangular coordinates. Let's look at, let's see, I need to scroll down. Let's look at some area and volume in polar coordinates. There we go, that looks a little better. So how to find area and volume using polar coordinates. Let's consider this double integral. First of all, I want to describe the solid whose volume is being given. So let's look at the region in the xy plane. We have y is going from negative square root of 4 minus x squared to positive square root of 4 minus x squared, and x is going from negative 2 to 2. So here's the region R that we are integrating over, and then if the function is 5, what we really have then is a cylinder. Up at 5, so we have, that does not look like a circle. A little bit more like a circle. And we have a cylinder, radius 5 here. No, not a cylinder radius 5. Cylinder radius 2, height of 5. Okay, let's evaluate the volume of this using geometry. So volume of a cylinder, the area of the base times the height, so that's pi r squared h, so that's easy enough. Pi times r squared. 2 squared times h is 5, so 20 pi. And let's set up a double integral for this using our rectangular coordinate system. Let's see here. Well, I guess, how do we want to do this? Let's see here. Begin to evaluate the double integral. Let's see. Well, we would integrate the 5 and get 5y. And we're going to evaluate that from negative square root of 4 minus x squared to positive square root of 4 minus x squared. That's all dx. It'll be negative 2 to 2, 5 times square root of 4 minus x squared minus negative square root of 4 minus x squared dx. Okay, that looks like negative 2 to 2. That'll actually end up being 2 of those. So 10 square root of 4 minus x squared. Let's pause the video for a little bit to think about an integration strategy that you could use here. I mean, it probably is easiest just to use area. That's 10, and then it's a circle, or a half semicircle. Otherwise, you'd be stuck with trig substitution, or maybe an integration formula, if you're going to do that by hand. Let's instead, let's look at the initial region and just kind of set up the region, not the integrand. There's actually more to it, but just set up the region and get the limits of the integral using polar coordinates. We had 2, right, as a circle radius 2. Well, all that is, and you can do whatever order you want, there's something inside here, we're not sure. It's not quite as simple as just integrating that same function. We'll see that soon. We're going to derive what that is. Well, let's do dr first, d theta. Doesn't really matter. Usually we do r first, but you can do it either way, depending on the context of the problem. But here you can see r just goes from 0 to 2. If you think of that, it's just r starts at 0 and goes to 2. And then theta starts at 0 and goes all the way around to 2 pi. And look at those limits, constant limits. It's like integrating over a rectangle. So if you have a circle as your region and you're integrating over a circle, polar coordinates might actually be much easier. All right, so one more comment here, and then we will move on to the derivation of integrals in double integrals and polar coordinates. When we first did this, we kind of developed this graphical meaning of the integral as volume. But we also looked at this a little more carefully and we said, well, we could take this region and partition it in terms of x and y. Partitioning the region R with increments of x, delta x sub I, and increments of y, delta y sub I. And then if we have infinitely many products where we multiply the delta x, delta y, and then we multiply by the height, we get these little rectangles. F of x sub I, y sub I, delta x sub I, delta y sub I. We get a tall, let me move over. Try this one. I can't see where that one went either. Hold on, we need to zoom in. Let's cheat and zoom in. All right, let's go here, up, maybe we'll up there. Some curve here. And we can approximate this with a little rectangular prism and find its volume. And so if we add all of those up, the sum, how do we want to word this? I goes from 1 up to n, f of x sub I, y sub I, delta x sub I, delta y sub I. But then we take a limit as the biggest one goes to 0. That was that norm, if you recall. The limit as that goes to 0, what we would get then is that would be the volume of the whole thing. And so we've seen that volumes here can be computed as iterated integrals, where we integrate some function f of xy. If we integrate dy first, it's like from some function of x on the bottom up to some function of x at the top, and then we integrate x from, say, a to b. In which case we see that cross-sectional area, and then we fill that out under the volume. We fill that volume under the surface. So we wanted to refresh this because now we want to look at, okay, what will this be in polar coordinates? What will this look like? So let's take a look now and kind of revisit that process of if we partition it, how do we partition it in polar coordinates? When we have this thing that's going up, it's not a rectangle. We'll see what it looks like. And so it's a little bit different, but the development is going to be similar. Instead of partitioning in terms of x and in terms of y and ending up with rectangles, what we would do it instead is we'd cut arcs and then have different rays coming out from the origin. If we think of our partition, we have x and y. We have some outer curve, some inner curve. Call this R1 equals, or sorry, R equals G1 of theta. That's like a inner function, and then R equals G2 of theta. And then we have two different angles. We have like an alpha, and let me move in a little bit, alpha, and then beta. So we have one angle and then the other angle, right? And then we have the partitioning kind of cuts this up into different rays. Let me do the partitioning actually in a different color. What would be a good color here? How about green? So we have different rays coming out, and then we have different arcs coming out from that will be like circles, be parallel circles there coming out. And if we pick one particular one here, we want to look at what the partition would be, what that area of the base would be, and how would that relate then to the volume that gets projected above that. Now the key here is that that partition looks like a little slice of it. It's like a little sector there. So let's kind of figure out the area of that shaded region, see if we can come up with a formula for that. One way to think about this is it would be, let's see here, we need some more labeling. We need two different radii. So we need an r sub I and then an r sub I plus 1. And then we need two different angles. We'll call it theta sub I and then theta sub I plus 1. So the way we're going to develop this is you can imagine, I'm going to try to draw on my sector here, two circles, trying to be concentric circles. And so we take the outer circle, subtract the inner circle. That's too much though, but that's pi times r sub I plus 1 squared minus pi times r sub I squared, right? Inner radius, outer radius. the r sub I, and then the next one. But we don't have the whole ring. That would be the whole ring. We just have a portion of the ring. And the way we get the portion of the ring is we just subtract the two angles and then divide that by 2 pi, and that will get us the portion of the full circle. So we're going to call that delta theta sub I over 2 pi. The first part here is the area of the full ring. And the second is, that's finding the percent of the ring that we want. Now we're going to try to simplify that. Let's see here. We could factor out a pi, and then r sub I plus 1 squared minus r sub I squared. And then we have delta theta sub I over 2 pi. Let's see here. Let me do r sub I plus 1 plus r sub I, and r sub I plus 1 minus r sub I, times delta theta sub I over 2 pi. I think I need to move over. You'll notice we lose the pi's. It's kind of interesting. Let me combine the r sub I plus 1 plus r sub I and put that over 2. Let's call the r sub I plus 1 minus r sub I, that's just difference in r's. Let's call that delta r sub I. And then we have delta theta sub I. And you'll notice here the r sub I plus 1 plus r sub I over 2, that's like the average, right? And so, but we're all becoming infinitely small. And so it's not crazy to say that that's going to be approximately r sub I, especially as our delta, our norm gets smaller and smaller and smaller. We're going to say this is approximately r sub I times delta r sub I delta theta sub I. That is the area of our representative piece. Now, if you recall, the area of our representative piece up here, that delta A sub I would be delta x sub I delta y sub I. It's a rectangle. Delta A sub I delta x sub I, it's a rectangle. But here, it's dependent on the r. The further out you go, the bigger that gets. You can kind of imagine here as you go out, right, they get bigger and bigger and bigger. So they get scaled. So it's not, let me go back up here and feel like I'm getting distracted, but back up here where we rewrote example 2, we rewrote the integral. And we said, well, the limits in polar form are pretty easy. R goes from 0 to 2. Theta goes from 0 to 2 pi, and then we're done. But it's not that dy dx just gets replaced by dr d theta. Dy dx is the area of the rectangle. We need a corresponding area of that represented sector, and the way we do that is this r dr d theta. So the full volume will be, let me just write it here. Thus, we'll have the integral, and we have some f of, now it's f of xy, but x is r cosine theta, r sine theta, and then r dr d theta. And then we're integrating r first, so it would be from the inner function, which would be whatever g1 of theta is, to the outer function g2 of theta, and then the angle goes from alpha to beta. Follow all that, hopefully? Hopefully that made sense. This is a formula. You want to write this down on your formula sheet. Hopefully it will make more sense when we do some more examples, but this video is already pretty long, almost 20 minutes. So we're going to stop right here, and then we will make another video for the rest of this section. If you have any questions, comment below, post them in the Discord chat, or email me, and we'll try to clarify.